Okay, good morning, everybody. So today is the first lecture where we start to actually talk about the object-oriented part of Java. So we're going to start implementing our own classes now, where you're using the classes to actually make objects. So far, you've implemented some classes, but you haven't been making objects using those classes. So to begin, I'm just going to quickly review some fundamental terms to make sure everybody's clear on these terms when I talk about them. All right, so remember what a type is. So a type is just a set of values and the operations that you can perform with those values. Right, so for example, an int, it's just the integer values between integer min value and integer max value. So those are your set of values. Right? What can you do with an int? Well, you can do arithmetic with an int. Right? Similarly, you've got your reference types. So you've got something like string. A string is any sequence of 0 or more characters. So there are your set of values. What can you do with a string? Well, we saw strings had some methods like index of, char at, substring, and so on and so on and so forth. Right? So a class is just a user-defined type, or is a user-defined type. And similarly with list. Right? So Java's got your primitive types, and Java has reference types. Right? So your primitive types are the types that are, quote, built in. Right? So any type that begins with a lowercase letter, you know is a primitive type. Right? So they represent the numeric types in Java, and they represent the type true, false. Finally, you've got your reference types. So anything that's not primitive is a reference type. And that means arrays are also of reference type, right? Even though they don't necessarily look like that. So if you make an array of int, right, the elements inside the array are primitive, but the array itself is a reference type, is actually an object, right? So it's a reference type. Right, and we've seen string, we've seen array list, and sets and maps already. So classes are just implementations of a reference type, right? So they're user-defined types. So in Java, a class is a type. There are types also that are not classes, right? So there are things called interfaces as well. That are also types. Right? So array list is a type, string is a type, they're both classes. This thing called list is a type, but it's not a class. Right? So it's something called an interface. And finally, objects are just instances of a class. Right? So like the number 5 is an instance of an int. Right? If you make an array list object by writing new array list, by calling the array list constructor, you end up with an instance of an array list. So the one way to think about objects is that an object is just a copy of a class, right? So you use the class to make, as a blueprint, to stamp out or to produce objects, right? So when you make an object, you can think about, one way to think about it is like you're making a copy of a class, and you're using that copy to, as your object. All right, so these things called reference types, they're called that because a reference type variable stores a reference, right? So a reference is just something that lets you identify a particular object. So in Java, most implementations, references are memory addresses. So they're like pointers. Right? Any variable whose type. Right, so we said that t is a reference. Right, so here, that variable t, because t is a reference type, right, so t stores a reference to an array list object in this particular case. Right, for C programmers, you can think of it as t is a pointer to an array list object. Right, it lets you find that object in memory. All right, so to make this clear, you can sketch out what's called a memory diagram. So a memory diagram is it's just a table. Right? It's got 3 columns, right? And it's supposed to be a picture of what's in memory. And so in our right-hand column, we've got something called the value. Right? So that's the actual value that's stored in memory on your computer. Right? When you store a value here, you're only allowed to store one thing in each square. Right, so I can put one thing there, I can put one thing there, I can put one thing there, and so on and so on and so on. For our purposes, it will always be a number. Right? So after all, in your computer, everything's just bits, right? So just ones and zeros. So we can just interpret these values as numbers. The middle column is going to be the address. So I'm just going to label the blocks or the square or the rectangles, I guess, from 0 up. So you can think of the address as just being an index, right? So if you imagine that this is an array, that's the index into that particular array element. And finally, we want to sketch out memory, so we have variables in memory. So the first column is if we have a variable and it has a name, we'll put the name in the first column. Right? And so the difference between a primitive type and a reference type is shown in this picture here. Right? So imagine you have a little program. It makes a variable x, whose type is double. So in memory somewhere, that thing x has to be stored. Right? You can put this wherever you want. It doesn't have to be where I'm showing you right now. Right? So you just pick one of these rows and you label it with x. Right? So x happens to live at address 100. Right? What value is stored in memory? Well, the value is actually -1. Right? So for primitive types, you store the actual value. On the next line, we have a variable t. So t appears somewhere in memory. Right? We're going to put this at address 101. Again, you can put it wherever you want. It can't overwrite an already existing variable, right? So you can't put two things on one row. So we have a variable t. We're going to arbitrarily put it at address 101. Right? Now on the right-hand side, it says new array list. And so what's sitting in memory here is not the array list object itself. Rather, it's a reference to the array list object. The actual array list lives somewhere else in memory. Right? So here, I've stuck it at address 700. Right? I've labeled this box here with its type rather than a value, right? Just so that we know that this happens to be an array list object. I don't know what's actually here, right? So I have no idea how the array list class is implemented or what it looks like in memory, right? And I don't actually care, right? All that I care is that the array list object is here at address 700. Right? You can kind of guess that there's probably an array that holds the elements of the list, but we don't know that for sure. And so so what value does t store? Well, t stores the address of that object. Right? So when you see something on this memory diagram that has an a after it, that's indicating it's an address and not a numeric value. Right? So 700a means the address 700. Right? On the next line, we make another variable u, and we say u gets the value of t. Right? That's what the assignment operator means in most programming languages. Right? It means that thing gets the value of the thing on the right-hand side. Right? And so what are values in Java? Well, it's this column sitting out here in this third column. Right? So when you say u gets the value of t, then u literally gets the value of t. So the value of u is also 700a. What does that mean? U and t both point at the same array list object. And so it's like if you had a pointer in C and you made a copy of the pointer. Right? That also, you now have two pointers that point to the same object. Here we've got two references that refer to the same object. Right? If you ask t to add an element to the list, right, it's that array list object whose size grows. Right? If you then ask u, how big is the list? Right? Well, u will also say that it's gotten one bigger because it also refers to that list. Right? So changes made to the object via t or u, the other variable can see those changes. Right? Because it points to the same object after all. Right? And so that's the difference between a reference type and a primitive type. Right? Primitive types store the actual value. Reference types store a reference to an object. Right? I guess I should point out, when you use the variable t, right, it's slightly slower than using the variable x. Right? Because using the variable x, all your computer has to do is go into memory beside the box labeled x and get the value. Right? If you want to do something with t or u, right, your CPU has to do at least one extra step. Right? It sees that the address here is 700, so now it has to jump into memory to find the object that it corresponds to. Right? And so there is this extra step or one level of indirection that has to be made when you use a reference type. The same thing happens in C when you use a pointer. Okay, so there are the fundamental terms. It's pretty important that you understand the fundamental terms and that you get them clear in your head. Otherwise, concepts that show up later on can be a little bit confusing. In particular, this difference between a reference and a primitive type. It's pretty important to get that straight. Otherwise, when you start to use objects and start to create your own objects and classes, you can run into unusual bugs, which are hard to understand unless you remember what a reference actually is. Okay, so now we start actually talking about object-oriented programming. So the people who study programming languages, and in particular object-oriented programming languages, like to refer to something called the object model. Right? And so this is a way of thinking about object-oriented programming languages in general. Right? So when your C courses, the C programming language is largely a procedural programming language. Right? So in the C programming language, you focus on breaking down programs into C source code files. In those source code files, you've got functions. Right? You pass information to the functions can operate on that information. They can return values back to you, or they can modify the information. In object-oriented programming, you break your program down in a different way. Right? So instead of breaking things down into functions, you break your program down into objects. The objects themselves, they contain data, and those objects can operate on their own data. Right? And so in other words, you can ask an object to do something and you don't have to pass it any extra information, or you don't necessarily have to pass it any extra information. Right? The information that it needs to operate on is already inside the object itself. And so there's four main elements of this model. So there's these terms here. I'm not going to talk about the fourth one right now. I'm just going to quickly tell you what these three terms are at a high level. We're not going to spend any time actually studying them in any great detail. Okay, so part one of the model is this thing called abstraction, right? And so you can read that quote there. Basically, the idea behind abstraction is that as a programmer, you generally don't care, or you don't want to care about the details of how something works, right? So for example, when you're using an int in C or Java, it doesn't matter, right? You don't care how the computer is adding the numbers, right? You don't care how the int is represented in memory, right? There's a whole bunch of stuff you don't care about. You just care that it's an integer and you can do stuff with it. Right? So the same thing is true in object-oriented programming. Right? You want to ignore everything that you don't care about at this particular moment, right? And you only want to focus on the stuff that is important right now. Right? So in your data structures course, you should have been told that there's this thing called an abstract data type. Right? So notice the word abstract again. Right? So an abstract data type is something like a list. So a list, what can you do with a list? Well, you can add stuff to a list. You can remove stuff from a list, right? You can use an index maybe to get something from a list, right? And then you are told, how do you implement a list? Well, you can use an array to implement a list, or you can use a linked list or a linked sequence of nodes to implement a list, right? And so there's many different ways that you can actually implement the list, right? The abstract data type is this thing called list, right? So you know the operations that you can perform with a list, but you don't know how it performs those operations. Right? And so that's the idea in abstraction, right? So I don't care if I have a list, right? I don't care how the list is implemented, right? I just care that you have a list. Right? Now in C, you don't really have that flexibility, right? So in C, you implement a list, you pretty much know, if you implement a list, you either get a linked list or an array-based list, right? And you know it's a linked list or an array-based list, right? There's not really any way to avoid knowing that that is what it is, right? If you write a function that takes in a list, then it takes in either a linked list or an array-based list, right? But it can't take in either one and still work. In these object-oriented programming languages, abstraction leads to something called substitutability, right? So in other words, I can say a list has these operations, right? Add, get, set, size, and things like that, right? But you don't care how they're implemented. Right? And so that lets you substitute different list implementations. You write a method that accepts any kind of list, right? And it doesn't care how that list is implemented. Right? So for example, in the collections class, there's this method binary search, right? That performs binary search on a list. Right? What kind of list? It doesn't matter. It can be an array list, it can be a linked list, or some other kind of list. Right? It works. Why does it work? Because of abstraction. Right? whoever wrote this method is basically telling you, hey, look, I don't care what kind of list this is. You can give me any kind of list you want, right? And this method will still work. Why can that work? Because the list, in this case, it's an interface, right, says what methods all lists must provide. Right? So whoever wrote binary search can write that method using whatever methods, can implement binary search, using whatever methods the list interface has. Right? They don't actually care how that list gets an element or sets an element. And so that's the idea behind abstraction. This idea exists, in all programming languages, right, even C, right? But in the object-oriented programming languages, it leads to being able to substitute different types as needed. Okay, encapsulation also exists in most programming languages. So the idea in encapsulation is that you can compartmentalize the elements of an abstraction that constitute its structure and behavior. So what they're saying here is that you can, every abstraction has data, right? And it has some sort of set of operations that you can perform, right? In encapsulation, you take the data and the behavior and you put it into one place, right? And ideally, you hide the data behind the behavior. Right? And so in Java, what ends up happening is the obvious place where encapsulation occurs is you make a class, right? That class can have data in it, right? So the class can have variables, right? And the class has a bunch of methods that operate on the variables. Right? So encapsulation serves to separate the methods, so the contractual interface, right? The methods of a type and its implementation. Right? So you can see what the methods are, but you can't necessarily see how the methods are implemented or what information they are operating on. Right? And so this leads to the idea of information hiding. Finally, there's this thing called modularity. So modularity just means breaking down a program into parts. That's all it means. Right? How do you do this exactly? It turns out there's many different ways you can do this. Java has at least 3 main mechanisms for implementing modularity. And so modularity is the idea that you organize your program into individual components, right? And then you place these components in certain places. So in Java, you can break your program down into classes, right? You can put your classes, you can organize your classes into packages. So we saw packages in the first lab, right? And then there's yet another level of modularity in Java, the thing called a module that we don't talk about in this course. All right, so how do these things look like in an actual Java program, right? So it's useful to look at what does an actual Java program look like. So your actual Java program is typically split into 1 or more files, right? So if you have a small Java program, it's 1 file, right? If you have a big Java program, it's thousands or tens of thousands or hundreds of thousands of files. It's also similar to C, right? Small C program you can put into 1 C source code file. If you've got a bunch of types that you defined yourself, then they go into their own C source code files. Well, ideally, they go into their own C source code files, right? But there are 1 or more files in a typical Java program. At the top of each file, there will be 1 or more package names. Right? So in our labs, everything's been in a package so far, I think. Right? So package lab 1, for example. Right? So the package mechanism is one of the mechanisms that Java uses for modularity. Right? It lets you organize your classes into separate packages. Right? If your class needs the capabilities of some other type, right, then you may have to import that other type. In particular, you have to import the other type if it lives in a different package. So up here, you might have 0 or more import statements. Right? And then in the simplest type of Java file, there's 1 class. Right? Inside that class are the variables that are part of your class. Right? And so Java, these are called fields. Right? So these are or class variables. Finally, you can have, not finally, every class is allowed to have 0 or more constructors. So we haven't seen these yet. We haven't implemented these yet. You've used them. So when you write new array list or new string, you're calling a constructor, right? Where do those constructors live? They live inside the class. And finally, your class can have 0 or more methods. So whenever you call a method, where do those methods live? Well, they're also defined inside of a class. And so there's a picture. So the details here don't matter. So if you can't read it, that's fine, right? This is just trying to show you a picture of what a typical class looks like. Right? So at the top, you've got a package declaration. That's followed by 0 or more import statements. Right? Then that's typically followed by your class. And inside your class, there are fields, constructors, and methods. Right? And so that's what a typical Java programs look like. A typical Java class looks like. And it's actually much more complicated than this, but we don't have time to talk about all this extra stuff. Right? So there's many, many, many other things that can appear in a typical Java program or in a Java source code file. Right? The only one of these things that you're going to see is in this course is that one right there. So later on, we're going to put a class inside of another class. Right? But typically, for most classes, that doesn't happen. Right? Most classes, they stand on their own. And you don't have another class defined inside of them. Right? And of course, the Java language evolves at it's pretty rapid rate now, actually. So the company that manages Java now says that there's a major update every 6 months, which is fast for a programming language, right? C updates like every 10 years or something like that. Java updates every 6 months. So they're constantly adding new stuff to the programming language. If you want to know more about this, you can click on that link there. That's the standard tutorial that talks about these kinds of things, right? Okay, so what are these things called? Packages. Well, we saw them in Lab 1, right? Packages is the package mechanism in Java is just a way to organize Java classes into these things called packages or namespaces, right? So a namespace is just a container for names. So that's all it is, right? So you saw that in Lab 1, the packages, they're just directories, right? So every directory has a name, right? And inside every directory, you can have more directories, right? So that's what this thing here means. It's a container for names, right? So every directory is just just a container for other directories. Right. So the reason you use packages is because when you're creating classes, you'll often create more than one class, and they're meant to work together. So they're all related somehow. And so if you look at the Java, the way that this Java standard library organizes its classes, all of the standard library classes, they go into the package called Java, which kind of makes sense, right? These are parts of the standard library. We'll put them in this thing called Java. Right? Now, you don't want to put all the classes in Java that the Java standard library provides just inside one directory or in one package. Right? You now want to organize those classes as well. Right? So you can create a package inside of another package. Right? You can make a folder inside of another folder. Right? So, for example, the fundamental Java classes are in the package called lang, right? Short for language. Right? So java.lang, that's the full name of the package lang. Util contains the classes that are useful to many programs, right? Utility, right? So java.util is the full name of the util package, right? IO is the package that stores the classes that work that deal with input and output. So file input and output or network input and output. Right? So the full name of IO is java.io. Right? The full name is called the fully qualified name. Right? So it's just the list of packages with a period separating the individual subpackages. Right. Inside any package, you're allowed to put a class. So the string class and the math class and the class called big O object, those are all fundamental to the language, so they go into java.lang. Right. And so when you put a class inside of a package, the class now has a full name as well. Right? So the full name of string is actually java.lang.string. Right? So it's the full package name followed by a dot, followed by the class name. Right? And so that's the fully qualified class name. Right? The fact that the class name actually has a full name, right? So the list of packages leading up to the class is there to help ensure that all class names are unique. So you can have a java.lang.string, right? But there's nothing from stopping you from making your own string class, right? And putting it into your own package, right? And now you can use both string types in your program at the same time, right? Because they have different full names. Right? And so the idea is that you can do something like make a package called your and make your own type called string, right? And you can use your .string class in your program along with the standard string class, right? You just have to make sure that one of the types, one of the string types that you're using, you're always using the fully qualified name, right? So to use your string, you would write new your string, right? To use the regular string, you would just write string, right? You might have someone else's string library as well, and that would be in a different package. If you wanted to use that in your program, you use their package name followed by their string type, right? And now you can have multiple types, all called string, right? All having the same name in your program, right? This is a big problem in C, right? So in a big C program, especially if you start to use other people's libraries, right? In C, all the names have to be unique, right? And this includes the function names and variable names at global scope as well, right? So you can't have a global variable called A and a function called A as well in the same program, right? It doesn't work when you try to compile it, right? Similarly, you can't make a type, if you have a type called list in your program and you decide that, hey, I need someone else's list type, if that other person's list type is also called list, you're stuck. You can't use it in the same program, right? It doesn't work. And so the package mechanism is Java's way of getting around this unique name problem. Now the problem is that the compiler doesn't know or doesn't care what you name your packages really, right? As long as it's a legal package name, it's happy to accept it, right? And so that means that even though this mechanism exists, it doesn't actually guarantee that class names are unique, right? There's nothing from stopping you from making a package called CMPE212, right? And somebody else making the same package and putting the same classes in those packages. Right? Now when you try to go to use those at the same time, they don't have unique names anymore. And so in Java, there is this convention that's supposed to be used called the package naming convention. So the idea is that you take your domain name and you write down the pieces of the domain name in reverse. Right? And so the computing science domain name at QueensU is cs.queensu.ca, right? That's just the URL that you use to get to the computing science homepage, right? So the idea is you write it in reverse, so ca.queensu.cs, so that becomes your package, that becomes your package name, right? If you're looking at the source code for the course, then this is the package naming convention that's used there, right? Everything's in ca.queensu.cs.sysc124. And so that's the convention that's used. These are guaranteed to be unique because there is a central registry of domain names. Right? So there's some organization that's responsible for making sure that no one makes the same domain. So there's no two domains on the internet are the same name, have the same name. Right. So that's packages. We know what an import statement does, right? And so the next part is, well, what's in a class? So a class is just an implementation of a type that the user is allowed to create, right? User-defined type. Right? Most classes, not all, but most, are used to create objects, right? So you take what the class defines, you use that as a blueprint, and that produces an object of that type. Why do you want to make types? So why can't I just use a class? Like, why do I need objects, right? And so the idea is that every object is allowed, gets its own copy of all of the non-static variables that a class defines, right? So each object gets its own copy, right? And so what does that mean? That means you can have multiple objects all having the same type, but they have their own information, right? So in other words, you can have 10 different list objects that all contain different elements, right? If you made a matrix class, you could have multiple matrices that all have different elements. Right? So this term state, we say that the state of an object is the set of all the current values of its non-static fields, right? So you look at the variables that the object has, right? Whatever values those variables have, that's its state, right? So for example, if you wanted to, point 2. So we saw that point2 class last lecture or a couple of lectures ago. Right? So remember the point2 object, or the point2 class represents two-dimensional points. Right? So the point has an x and a y coordinate. Right? If you were to write code like new point12, new point -38, and new point 513, right, you actually get 3 different point objects. Right? They all have their own x and y coordinate. Right? So when you use a class for the first time, so if this is the first use of point2 in my program, the Java virtual machine loads the class into memory. Right? So your point2 class shows up somewhere in memory. Right? And you'll see shortly that inside the point2 class, there's a variable x and there's a variable y. Right? X is the x coordinate of the point, y is the y coordinate of the point. Right? When you write new point2, right, that looks at the class and makes a copy of the class and plunks it down somewhere in memory. Right? So that first new point2, right, takes the point2 class, copies it into memory somewhere, right, to produce a point2 object. Right? So use the class as a blueprint to produce an object. Right? The constructor, so this is a constructor call, right, has the values 1 and 2. So the constructor fills in the values 1 and 2 of the newly created object. Right? So the job of the constructor is to initialize a newly created object. Right? So the constructor fills in the values 1 and 2. Right? And then new returns the address of the newly created object, which we store in P. Right? So there's our variable P. It's living somewhere. Right? Client just means it's the program that's running. Right? Beside P is the value 600A, which means that P refers to that point there. Right? On the next line, we do new point2 minus 3 and 8. So new point2 copies the class, plunks it down somewhere in memory, fills in the values minus 3 and 8, then returns the address 700 back to the caller. Right? So the address 700A gets stored beside Q. Right? And the same thing happens for the third point. Right? So new point 513, new copies that point, plunks it somewhere down in memory. Constructor fills in the values 5 and 13, and then new returns the address back to the caller. So we store that in R, right? And R now refers to the point at address 800. Okay, so to implement a class, we're going to mostly implement these things called value classes. And so many classes, not all, but many classes represent like different kinds of values. Right? So for example, a name or a date, right? Colors, points, vectors, matrices, right? Strings, dates, integer, lists, things like that. Right? So whenever you implement a class, not necessarily just a value class, right? Whenever you implement a class, you have to decide what values do you want your objects to store. Right? So for example, if I'm implementing a class for colors, right, how am I going to store the information for that color? Right? For a point, what variables do I need to store the information for that point? Right? And so on and so on and so forth. Right? You're going to store the information in variables. So the variables that represent the state of an object, Java calls those fields. Right? So a field is just a variable that belongs to an object. So let's implement the point2 class. Right? So we want a two-dimensional point. It has, it's supposed to represent a real point, right? So it has a real x and a real y. Right? So you ask yourself, well, okay, so what variables do I need to store the x and y coordinate of a point? Right? So the obvious answer is, right, well, I need a double value for the x coordinate, and I need a double value for the y coordinate. Right? There's a less obvious answer, right? You can use an array. So an array of two double values, right, and store the x and y coordinates in the array. You could use a list, right, and store the two values inside of a list, right, and so on and so on and so on, right. The representation of your point is not unique, right? So there's no one right, there's usually not one right answer to do this, right? There's often many, many, many different ways that you can do this. But the obvious way for points is to create an x and a y, a variable x and y. Right. So if you look in this package here, you'll find the point2 class. Right. So when you make your class, right? You use the keyword class to indicate I'm making a class. Right? You give it a name, right? Remember, class names should always be capitalized. Right? If you want other people to use your class, you're probably going to make it public. Right? Then your braces, right? And then most Java programmers, they put the fields or the variables at the top of the class. Right? So what do I need to represent a point? Well, I need an x coordinate, I need a y coordinate. That's going to be of type double and double because I want real points. When you declare your variables, you're allowed to say, you're allowed to specify what access those variables have. So you can specify what's called the access modifier here. Right? And so you've got 4 choices for your access modifier. Private means that the variable x is visible only inside point2 itself. Right? So outside of the point2 class, if you make your variable private, then outside of the class, x is not visible. Right? So in other words, if you have a point2 object and you try to access the x coordinate of the point directly from outside of the class, right, that's not allowed. Right? It's not visible from outside. Inside the class, x is visible. So anywhere inside point2, you can use the variable x. Right? And the same is true for y. So in general, if you have no other reason, or if you don't have a good reason, then you should make your variables private. Right? And so that minimizes the visibility of your fields. So it minimizes the visibility of x and y. Right? And that will help to minimize any errors that might occur when other classes access those fields directly. Question?
How is it hiding the address?
So there is no address in this particular case because these are primitive types, right? So you don't even, and Java doesn't even care about the address of x and y in this particular case, right? The access is controlled by the compiler, right? So the compiler reads a program, right? When it sees the point2 class, it knows that x and y are private, right? And so when it reads the rest of the program, right, if there's another class somewhere else that's trying to access x and y directly, it will not compile, it will refuse to compile the code. It'll flag that as an error and it'll say x and y are not visible at this point. So that's it, right? So it's a compiler thing. Right. So generally, you should make your fields private. If you need to make them more visible later on, you can change their visibility later on. Okay, so a top-level class is a class that's not defined inside of another class. Point2 is not inside of another class, so it's a top-level class. Right. The class itself, a top-level class can have exactly one of 2 access modifiers. Right. It can be public, which is the usual thing. Right. So public means every other class can see this class. That's normally what you want when you make a top-level class. Right. You can, however, have what's called, so you can have no access modifier. Right. So if you leave public off, then this class is said to be package private, or is said to have package private access. Package private means the class is only visible inside the package itself. Right? So if I was to strike public from here, then point2 is only usable inside of that package there. Right? And exactly that package. Right? If you make a subpackage of geometry, point2 is still not visible to that subpackage. Right? So package private means exactly visible in this package and only this package. Right? So the reason you might want to make a package private class is because you want to create a, for example, point2 might need the help of another class, right? But that other class is not useful to anything other than point2. Right? And so then in that case, you might make that helper class visible inside package private so that point2 can access it, but no one else can. Right? And so this is another idea that's going to be new to C programmers, right? In C, you can't easily hide the visibility of anything, right? In Java and many other object-oriented programming languages, you are able to control the visibility of certain things. Okay, so what about our fields? So your fields, you can have 4 access modifiers. Right? So private is the access modifier that you're normally going to use. Right? The field is visible only inside of the class itself. Right? If there's no access modifier, so if I strike the private here and just leave it blank, then X has package private access, right? So the field is visible to all classes inside of the same package, right? So if there's another class inside the same package as point2, it can go into a point2 object and get the X value directly. Protected means that the field is visible inside of the class, inside of the class, inside of the package, and to all things called subclasses. And so we're going to look at subclasses later on in the course. So for now, you can forget about protected, right? It's not relevant for our purposes right now. Public means that the field is visible to all classes everywhere. So if we have a public field, if we mark that field, X as being public, then anybody that gets a point2 object can get access to the X variable directly, right? So they can look at the value and they can change the value directly. Generally, you don't want public fields, right? If you have a public field, then objects have no control over the value of their state, right? Anybody can come in and change the fields. Okay, so the safe rule of thumb: if you have a constant, right, and you want that constant to be visible to everybody else, then make it public, right? So for example, pi and e in the math class are both public, right? Pi is a useful value for anybody using the math class, so it makes sense that people should have access to pi. It's constant, so no one can change the value, right? Imagine if it wasn't constant and public, right? Then someone come along, change the value of pi, and that screws up everybody that's using that field, right? If it's not a constant, then by default, you should probably make it private. And later on, we'll relax that rule, and you'll be able to use protected fields when you need to. Okay, so we've got point2, right? So there's our point2 class. It's got some variables in it. We don't have any constructors yet. We don't have any methods yet, but we'll add those in a minute, right? What about a different type of another kind of class, right? So imagine we want to implement a class that can count, right? So the idea is it represents like a physical counter. So you count in discrete steps of 1, right? So starting at 0, then you can count to 1, then 2, then 3, then 4. So it counts upwards, right? Sorry. So what fields would you need to represent a counter, right? So you ask yourself, well, all right, so what information do I need to represent an integer count, right? Well, I can probably get away with a single int in this case, right? So in that class, in that package there, right, there's a class called counter, right? A counter represents a device used to incrementally count upwards from 0 up to integer max value, right? So 0, 1, 2, 3, 4, 5, 6, and up to, right? So I need some variable to store the current count, right? So an int makes sense in this case, right? Give it a name, so I'm going to call it the value of the counter, right? And we'll make it private. Okay, so I kind of regret this example here, but we'll do it anyway because it's here. All right, so this one is considerably more complicated than the two that I just talked about. Right? So imagine you want to implement a class that represents a stopwatch, right? So it's a thing that the user can start the stopwatch, and it starts to keep track of how much time has passed since they pressed the start button, right? When they press the stop button, the stopwatch stops, and it tells you how much time has occurred since you last pressed start. Right? There's a lot of copy and paste errors. Sorry, that should be stopwatch. Right? And so when you stop and think, so when you ask yourself, so what do I need to actually represent a stopwatch? Right? At this point, it's not really obvious what you would do to represent a stopwatch. Right? So number one, you don't know how to keep track of time, right? Or at least how to keep track of time in Java, right? And so that's the first problem. So to solve that problem, this slide tells you how to solve that problem here. Right? So to get the current time in Java, there's this method called nanotime that's in the system class. Right? So nanotime gives you the most precise available system time in nanoseconds, right? So down to 10 to the minus 9. Right? Now it doesn't actually tell you, so you just get back some number, right? You get back a long value, right? And so it doesn't tell you what the actual time is. You just get back some long value. That long value is the amount of time since some arbitrary fixed starting time, and you don't know what the arbitrary fixed starting time is. Right? So every time you call nanotime, you get back some number that represents some time in nanoseconds. Right? But if you call it twice and subtract the two values, that tells you how much time has elapsed. Right? So if you call nanotime once to get the start time for the watch, so that's when you press start, right? And you call nanotime again when you press stop. If you subtract those two values, that actually tells you the number of nanoseconds that has elapsed between those two times. Right? So it looks like we can store the start time and the stop time for a stopwatch. Right? If I take the stop time minus the start time, that gives me the number of nanoseconds that has elapsed. Right? So my field called raw start time, that's the time in nanoseconds. Right? And raw stop time is the stop time in nanoseconds. Right. For the actual stopwatch, we're going to retort times back in normal seconds because that's what people normally think in. Right. Now, the stopwatch, so it tells you the amount of time that's elapsed between when you press start and stop. Right. But when you press start, that actually changes the state of the watch. Right. When you press start, that means the watch starts running. Right. And when you press stop, the watch stops running. Right. And so if you think about it for a little while, you're going to need to know, is the watch actually running, or has it been stopped? So you need some sort of field that indicates the state of the state that the watch is in. Is it running or is it not running? Right? And so there I can use a Boolean value, true if the watch is running, right, and false if the watch is not running. Right? So true if someone has pressed start but they haven't pressed stop, right, and false if if start has never been pressed. Or if stop has been pressed. Right? So now you need at least 3 fields in this particular case. Right? And you can go on and on and on with lots of these simple examples. Right? So if you wanted a rectangle, right, some sort of class that represents a rectangle, right, you would need to store at least some sort of information regarding the corners of the rectangle. Right? So you might need to store the coordinates of the upper left corner and the bottom right corner. Right? You might choose to store the coordinates for all 4 corners. Right? You could store the upper left corner, its width, and its height. Right? There's lots of different ways to do this. You could store the center point and the width and height of the rectangle as well. Right? There's many different ways that you can represent a rectangle. Okay, so what time do we have here? All right, so we haven't done anything yet, right? Our stopwatch class is just the class plus some fields. There's nothing else here, right? But you can actually use these the way they are. You can't do much with them, but you can use them, right? So you can make a class called makeSomeObjects. You can import, so that's wrong. That's basics.counter.bigCounter, right? You can import the classes, and now you can go ahead and make objects with those, using those types, right? So you can write new point2, you can write new counter, and you can write new stopwatch, and that program compiles just fine, right? Okay, so when you make a class like that, right, if you don't declare a constructor, so no constructor here, right, you get one for free, right? So the point2 class gets a point2 no argument constructor for free, right? Counter gets its no argument constructor for free, and stopwatch gets its no argument constructor for free, right? So in other words, when you make a class, you automatically, with no constructors, the compiler makes one for you, right? And that lets you write code like that, right? The compiler created constructor, if you have primitive fields like we do here, it sets all numeric values to 0, and it sets the Boolean values to false. So you get a stopwatch whose start time is 0, its stop time is 0, and is running is false. Right? You get a counter whose value is 0, and you get a point whose x and y coordinates are also 0. Right? So the class is usable even though we haven't done anything yet. And I guess I have to stop there because I think we're out of time. Yeah, it's 20 after. Right? And so we'll add some constructors and some methods in the next class. Right? Don't forget your labs this week. There's no lab, right? You have your quizzes this week in your lab. Right? So show up for the lab that you're supposed to show up for to write your quiz this week.